Hello guys, welcome back to this tutorial. Today we are going to talk about how to do the simulation, model sim. Using model sim here. It is in this example. As you know, if you have some um, FPGA, FPGA basics, you may know that we may take 20% of the time to write the source code. So, and 80% of the time for the simulation and debugging on the FPGA. But also, the simulation is very important. If you do the fully conditioned node simulation, it will save you a lot of time uh, to do the board debugging on the FPGA. So, if you are experienced FPGA engineer, you may have such experience that if your code is synthesizable, if you write a code, a lot, you know that what the expected synthesized the logic gate may look like. Yeah, most of the time when you write a code, you know what is going to synthesize as. If not, your code might be not understandable by the synthesized tools. So to write a synthesizable code is very important, right? So you cannot think like a C programmer or other programmer. You have to think yourself as writing the hardware code. Think of how thinking you are giving instruction to these synthesizer tools. How you want to organize the registers and flip flops, something like that. Okay. Um, Also, in the FPGA, logic gate is the lookup table. It's kind of like that. Okay. So okay. So if you already do the fully conditional synthesizer simulation, my experience told me that most of the time, it, um, the outcome on the FPGA would be exactly as same we expected when we run in simulation in the model scene. Okay. Okay, having talked about this experience, this tutorial is targeted for the experienced FPGA engineer. Okay, it's not a tutorial for teaching you how to write verilog code or how to do the simulation. I presume that you already have the basics, and this tutorial is more focused on how to deploy the algorithm to the FPGA. Okay, so as you may know, the 3D sensor, the algorithm itself is very difficult already. So I hope till now you understand the algorithms. If you don't, please leave your notes, leave your comments under below this tutorials. And I will try to make up for that if you make another video on that. As you know, I'm not a native English speaker, and also in the near future, I will try to do another version of it, and that's what I will speak in Chinese in the next tutorial, next version of this tutorial. Okay. So okay. So having talked about so much about it, let's start with today's tutorial. Now, this is the top model test bench for this module. I actually have several modules here. One is census transform module, and okay. So also after that the matching cost module, but you can comment that because it's already in the first when I did a simulation, I add modules one by one. Because it's still a Jeft motion, Jeft it's a draft version of my project, so I didn't write this simulation very organized, it, organized very well. So so but so just bear with me. Um, it's a little messy, but I hope you can read it. Yeah, hope you can read it. And also, you know that verilog code is very hard to read because it's parallel. So, but I try to write it module after module so that you can quite easy. People I think find it easy to follow. And most of our signals are self-interpretable. So so if you look, if you know the if you already read my algorithm part of the tutorial, you know what does that mean. Okay, LDPI, what does that mean? It's a math. Okay, okay. So okay, now you so in this GitHub in this GitHub repository, then you might find this simulation C. Okay, this is for generating data. Okay, this is for generating data. So here, stereo CPU. Under here, you can run. Let me run this. So what is CMake in the CMake file? So you the executable code, executable binary file is stereo CPU that corresponding to this stereo CPU. Okay, so let's run it. Stereo. Sorry, it should be inside this build, and inside this build I run this code in stereo CPU. If you don't give the input, you my code have to give you a hint that you need to give the arguments as a left image and right image. Okay, now let's give to left image 4, left 4, and right 4. So now that's one. Now it's doing the algorithm purely in C, so it may take a little time. This is a bug. Okay, ignore this. Ignore this. Because it's over almost 3 years, so I forgot a lot of details, and you can read the code and get rid of this code, this line yourself. Okay, so this is the disparity output. Okay, and this is the left image and this is the right image, but it's after rectification. Okay, rectification, after rectification, so that it generates this disparity output. Okay, so that is the what our FPGA is going to output. Okay, I give the FPGA a left and right image, then you have to, when I input and when I give it as a stimulus signal input, and the output from this source code should be this one. Okay, so now let's open the source code here. I think this should be here. Not this one. Your turn. No, it should be just wait a second, and let me find this code. Okay, so ignore this one. This one is very early one. Okay, in the GitHub repository, using this one. Okay, this one still they have time market at time 2020 200 2020, the last day of the year. So extract here, and you will see this one. Now let's open this the top model, which is a top model. Okay, so you know that this is rectified. After rectify, we get the signal. After rectification, we save the image in DDR, and then we get data from the DDR and transport and input this data to this module, census transfer module. Okay, so after all these processings, at last it should speed up this. Okay, this signal is a final output as a disparity map. Okay, it should be the disparity map of grayscale. Of course, disparity map is grayscale. Okay, so now let's jump back to this. So the way I do the simulation is that first we need to get the input data, right, which is a left image and right image. Here it's a assume that we have already rectified. Okay, because rectified module is the most difficult one, and this is most difficult, algorithmically complicated, because it's involved a lot of multiplication and division. So it's very complicated in terms of how to do the hardware math operation. Okay, so it's very challenging. Because I have updated several versions, I'm not sure this version is workable. You can check that. Yeah, I give you several versions. As I can remember that before I went to Singapore, that the last version it's not the final version, but I forgot to save the workable version, so you have to check one by one. I have several versions here. Rectify, float, this one. You have to check it yourself. Okay, this obviously this is not a optimal one, because you're using floating points that consumes a lot of multiplier results on the FPGA. So you have to check it out. Okay, so also there is some there's some stereo source code no rectified, or maybe you have to write it yourself. Okay, you have to follow my algorithm, and you have to rewrite this code yourself. Okay, so it's I will try to do that. In the last step, because I will only talk about this in the last step after I finish talking this the other modules, sensor transform, and then the matching cost. Okay, so also in the following tutorial, I will mainly talk about the algorithms, how to implement the algorithm in FPGA, and this is the only tutorial I talk about how to do the simulation. And yeah, because simulation is very hard to teach. Everyone has his own way to do the simulation. So this is my way. Okay, it's not a. I don't think it's a standard way, but it's workable. Okay, I don't have to. I don't know what is the standard way in the textbook, but as long as you can figure out all these bugs in your code, it's a good way to do the simulation. Okay, so this is my way of writing simulation code. Okay, I used to write the um, system verilog, but now I change it to verilog now. Okay, um, so I will briefly talk about the the pro, signal flow in this simulation. As you can see, then I'll read the image whole left image data into this register array as its source code, as the source of the left, and this another one is as the right image as a register array, because it's just a simulation. So the register array, actually you can have as much as you want, but in real FPGA you can't do that, because they take up a lot of resources on FPGA. You have to use the block RAM, or either using the block RAM or using the register SM. I forgot the right term for that. It's a register RAM. It's a RAM that consists is made of the lookup table, a special kind of lookup table. In both in Xilinx and Autora, they have. I guess Autora has a lookup table resource for that to build run as well. Okay, so okay. Now in the initial time, we also want to output the signal. This is the final output of the sensor transform of the left image, and this is the output of the sensor transform for the right image. Why do we need to output this data from the model scene? Because we want to compare this with the in a C file that we want to compare this software output with this simulation output. Okay. Also, comparison is one way, but in my way I do this verification. In my method I kind of like doing this things like this way. Wait a second. Okay, so this is the way I do the simulation. First, we input the data left and right image to the sensor transform in this software flow. Okay, and then we output the disparity. We have already seen the output outcome. Okay, this one, disparity in C, and now we have this verilog code of sensor transform. Now we input the same input image of left image and right image to this sensor transform verilog code in the model scene. So, and after we run the model scene, there will be output of this. There will be output of this sensor transform from the model scene, and then we input this output image file, output disparity output file from this model scene, as we can see here. This is the output. Okay, so this is a left image data from the model scene, which is the this one, sensor transform left, which is the output of the sensor transform. Okay, then we input it here to the rest of the model. Now this time we open this connection and to see whether we get the same disparity output here. Okay, so that's roughly the way I do the simulation. Also, you can compare one every data yourself. Means that every data from um, theoretically the output should be exactly the same, but in my code, because I didn't consider I didn't consider boundary condition. So in this census transform, there should be the boundary condition I need to take into account, but I forgot to take the boundary condition into account. But magically it's that the outcome is still quite good. So I kind of lazy, because to change the code you have to change it a lot. So I still left it as it is. Okay. In a future version of the code, I should take the boundary condition into account. Let me see, why is it census transform. Okay, this code. Okay. The boundary condition means that the image in the first of each row, the first pixel and the last few pixel, you have to take into account that because it's the streaming way. Okay, so that you need to pad 0 at the beginning or at the end, because okay. So I hope you get the idea. So you can rewrite this code yourself and do the simulation again. And then the outcome should be exactly the same. So you can use this code to do the simulation. Yeah, like this one. No. I guess we can run census versus golden output. Okay. The model scene census transform output versus the golden output. The golden output means this output. Okay, this output as is golden reference with this one. So you can compare every single data. Should be exactly the same. But as you can see in my situation, I have several in each row. There unmatched count is this number. So it's all because I didn't consider the boundary condition. Okay, so as you can see that the boundary the last few rows is all, the unmatched count is very high, but magically it still works. So yeah, I pointed out the the bugs in my code, but you can go in this direction to change that. Myself is just a little bit lazy, because at that time I quit my job to develop this prototype, and it takes me around 3 months to finish this prototype. So I'm facing the survival pressure, because I still have a family to support. I was very eager to want to get investments, so that I can have enough time to refine my code, and so that's why I didn't spend time to finish to update this one. But I guess I can left it as a homework. You guys can do that. Okay, as a practice. Also for the rest of the modules, as I have told you, that I'm not going to write this model scene. I'm not going to teach you how to write this model scene, and you have to do this yourself, uh, as a way of how I learned how to write verilog code. The day I graduated from the university, I was lucky to get a position from a startup company as a verilog verification engineer. So my first job was running this verilog test bench to test this each module, each no, each module. The guy who's one of the founder of the company, they write this each module, and he briefly tell me how what does this module mean, and the input and the output specification, and he already write this code, but there's a lot of timing errors. Timing errors logically, there are a lot of signals are not aligned with each other. So I have to write this model scene simulation code and to debug it one by to watch this to examine these signals in very detail to make sure that okay, so to make sure the signal, each signal are aligned with each other. So I have to find out I have to find out a way to write the right test bench, the input signal to locate the bugs in this code. Okay, so you guys are lucky because this has already verified by me. But I think I think it's not good for you guys to learn. Maybe I should give you some codes that have bugs inside, and you can debug it yourself. If you want to learn how to write variable code, a lazy way to learn doesn't give you much improvement. So, but I hope it helps you to learn as well. Okay, so. Okay, so I think that I would briefly talk about how. Okay, so also I forgot to tell you how to run this simulation, and this is a simulation code. Okay, actually you can generate this automatically, and then run to add these signals, add these waves you want to observe. But also you can you can save this yeah, you can save this wave dues. Okay, so Control plus X to save this as a wave dude. Okay, also you can rename it as alias. Okay. And then you do this wave do 1, and then it will open up the signal you want to observe each time. So to run this code is quite easy. But before that, you have to compile the Xilinx Zinc library to compile it for the simulation, for simulating or the simulation tool come with the Vivado. Okay, so now we can source and simulate such. Okay, first I think it should be this one. Compile it. After you compile it, kind of forgot which command to run. Compile. First you compile sh, okay, and after you compile, then you run the simulation, then you will get this. You will get this output, okay? And you just wait a little time for it to finish that. On this first model, it's run quite fast, but in the after you add more modules on that, the running time takes longer. Okay, it takes longer time to finish that. Okay. See, then I finish this running. Okay, so now after we finish the simulation, we have this we can get the output. I believe it is here. Simulation. We get this output. Census out. Okay. Census output. Let's check the top test bench here. Sensor transform left and right. Okay. Sensor transform. How come there's no? We should have the one. Not here. Let me check if it's. Did you write it? Yes, you have to change it. On each output enable clock, okay, each pixel you output this data to this file, okay, and let me see if the no, that means that it doesn't generate this data. Why it didn't generate? Pause at 19. Break mode a module aligned 901. Let me continue run this further. How come it didn't generate the output? Oh. Wait a second, don't tell me census transform. Okay, just like this one in this matching cost. Okay, in the matching cost module, you will have this census transform output left and right. Okay, if you open up, that's a huge file, and then you can, after you generate this file, after you get this file, and uh, you input here to the rest of the module, and you get the output disparity. Or you can do it to the module per module verification to compare each output, because theoretically they should be the same. If you take the boundary condition into account, you can use this compare, okay, to census compare to the golden output. Otherwise, continue using my way, my method to do the verification. Okay, so after each model, you read this the files, read this text output file from the for the model scene, and then input this output file to the next module, and run this verification code, and to see the output. Okay, then see if you still can run this code. I'm not sure. Verification. No. So okay, so that's the overall procedure how I do this simulation. Okay, now I hope that it helps you. Although it's very briefly, because I it's been 3 years. I forgot a lot of details, and I still trying. I still have other works to do, and I still don't have a work. I have to find a way to support myself. So I can only spend just I have to control the time, and spend a little. Ideally, I should only spend 1 hour each day on this project to get myself familiar with this project again. Okay, so okay, so thanks for watching. If you have any questions regarding to this project, you're welcome to leave your comments below. I will try to answer each one. Okay. Also, don't forget to get the source code and simulation code from GitHub. Okay. See you. Bye bye.